Welcome to ASRU 2021. Today, I'm going to introduce our work, multitask language modeling for improving speech recognition of real words. So this is a joint work with Linda Liu from Amazon, Anchor E, Anirudh, Dennis, and Ivan from Amazon Alexa Speech, and me myself from Georgia Institute of Technology. And this work is done as a applied scientist intern at Amazon Alexa previously. So first, we gonna have some introduction about how to design a joint language modeling with natural language understanding for multitask learning. And then we will propose a algorithm to optimize the coefficient for each subtask in a favor for multitask learning. In following, we will look at some baseline ASR system, language modeling methods, and dataset we are using in this work. We will show our experiments, conclusion, and some take-home message of this work. So first, why we learn ASR language model and why is the main target about this work? So we all know the goal about general automatic speech recognition is trying to reduce word error rates in general domain data. But one of the challenges how to dealing with those words are in a long tail distribution. For example, sports or some kind of information, we will not say so frequent, but during a conversation, we still want to mention those words, but we're trying to discuss with a intelligent speaker, mostly those words make the prediction become error and how to make this communication become smooth. So this long tail speech data and the general domain speech data is something we really care about in this work. And we want to propose the methods to improve recognition rate, which means reduce word error rate and long tail. And meanwhile, we hope these things can, in general, improve general domain speech data. So in terms of ASR language model, one of the idea nowadays is trying to have the output text with a language model rescoring. So the language model is trying to have a sequence pass rescoring from with a language model. So usually they just try to maximize the probability, which means to have a lower capacity. But in this work, how we trying to do is we trying to incorporate some common natural language understanding tasks. For example, intent classification, slot filling into this language model. And then after having this multitasking language model we are using for ASR rescoring. That is, this information can be per sentence, domain information, and per words nature language understanding tag. So it is a little bit hard to know how this language information could generate help recognition. But we all know ideally a strong recurrent network-based language model could be able to capture this long-range domain knowledge. So this domain information could be benefit from understanding the natural language on the NLU tag in our case. But you may think why this argument could be true. So let's have an example here.
Tell me about the hazard in Brugge, Belgium.
So this is audio example. People trying to ask for a smart speaker. For example, tell me about hazard in Brugge, Belgium. but it's a little bit hard for the recognizer to know whether these words like hazard is belong to a hazard event or belong to something else. For example, a soccer player. That is not just the text information or the phoneme information we have in a speech. We also have nano event, which we're trying to distinguish. And also the city information may help to trying to connect with this event. So this relationship as the knowledge could actually help recognize this sentence. That is saying we have a real world like hazard, and then we have the natural language tag. This can be hazard event, as we say, or the hazard was actually a soccer player in a club in Belgium. So that is one straightforward motivation to design this multitask like language model, because in most of our human or spoken language, the content information are much complicated and much straightforward. If we really look at those command level recognition, is easy to recognize, but one problem is trying to understand longer and much complex sentence which rich linguistic information. One common data set here is the 80s. So for example, they have the intent information and the slug information for each words, and still we have the utterance we're trying to recognize. So let's have some review in general ASR and joint training. So one problem is how to design a multitask network for language modeling, how to define and balance these joint training laws. What if the multi-label data is the limit? Do the performance gains coming from the joint training? So in this work, we firstly have a baseline RN transducer model, because we all know RN transducer is good for on-device processing and training and end-to-end processing with low latency. And what is the modification here is after the output from a RN transducer, we feed this text output to a multitask language model. And then they will have the language model score, and we will use the RNT score to jointly together combine this score to have the second pass rescoring, and finally have the text output. So there is some work in our team trying to have this efficient minimal word area training and different approach, but we basically trying to advance the design of our transducer. So what could be the neuron language modeling task? So one could be we can include the word sequence and each piece of the words. For example, if we have a sequence of words, the general idea for RN transducer is we have a jointly with the language model is we can have RN language model, which is trying to modeling these the words. And then the training loss of this language model is a negative log likelihood over m samples. And then finally, we have this the language model part, and then we go through with the somax from the latent embedding, and finally have the words outputs. Here, the L is on normal logic. CT is the hidden output context vector, and we have the word embedding and the bias based on this equation. So our architecture is straightforward. Is we have RNT cells, and for each cell we have the hidden embedding. But the embedding will have per words they will have the select prediction, and then for the all the embedding we will sum it up together to have intent detection based on another neural network. So we have the intent detection network, and also still a slot filling network. So, but one question here is how to balance the loss for each items. For example, we have our original language model loss. We also have the intent detection loss, but we also have the slot filling loss. So in the previous work, people trying to have a warn star and then uh, tuning this parameter from a small number. So we motivate by the same idea, but we use online optimization methods, which we're trying to do some efficient optimization on those coefficients. So the idea is based on randomized weighted majority algorithm on each of the weights. So you can think of we have three efficient one to turn. So each coefficient have an expert on it. And then the expert will modify this coefficient by the voting process. And then for each iteration, they'll motivate this whether to increase or decrease the portion about those coefficients after normalization. And then finally, these things will be converged based on a online optimization algorithm bounded by the regress. So we compare some previous work to have a schedule increasing intent contribution factor based on the previous study, and we find out based on this linear activation on this coefficient and the human tuning and the other meta-learning algorithm, this online optimization methods is much efficient in terms of the searching time. So next, let's look at some experiment setup. So first, we have our RNT, which is trained on 23,000 hours of far-field English corpora. And then for each LM state, we have our baseline language model without rescoring on the multi-label NLU dataset. And then we also transfer a pre-trained language LM corpora to the joint LM for multitask learning and evaluate its capacity from the transfer model. So this is trying to see if the pre-trained model can also benefit from this multitask learning. And finally, we studied the performance on two different task data, which is the general domain and the real-world domain. And we compared different methods in terms of the feature encoder. And we can also report some result for even each subdomain. So first, let's look at how could different language models help. From the beginning, due to the privacy reason, we normalized this capacity and to report these numbers after normalization. So we can find out by incorporating this intent detection and the self-filling, the words level information can much help when you're modeling a language model. And then jointly optimize these things, we can have a lower capacity, but with the weight majority algorithm, we can find the lowest capacity. And then when we're trying to transfer a large pre-trained data to this multitasking language data model with the small data, we can also find out this pre-trained language model with this additional LM and the slot filling task. They can help on the language model leverage upon this pre-trained information and have an even lower capacity here. And next, we can find out from the performance study, we reduce the word array relative. Also, due to this privacy reason, we didn't report the actual word error rate, but all the word error rate report here is lower than 10%. And we can find out this performance is improved by reduce this word array relative of 3.4%. And also, finally, we can see on the real world domain, this improvement in terms of the word error deduction is much larger, around 4.6%. And we also compare different attention encoder. We find out a projection attention, which is trying to have a residual connection between this attention can actually help in this NLU test. And we also find out for different subsets, for example, video, optimization, notification can actually help benefit from these multitask like language modeling, along with this ASR speech recognition. So finally, we have some conclusion here. So the joint training can improve the relative word error reduction. For example, 3.4 in the general domain and long tail domain for 4.6 compared with ASR only. And even with single task like language model, this knowledge-based like language modeling can actually help. And this weighted majority algorithm is competitive as a methods to balance these coefficients. And our result showing if we incorporate some feature model, for example, GPT-2 or those kind of very large pre-train, this performance can be even increased because of the foundation of the language modeling. And we also do some correlation analysis. We find out this per intent word error is correlated to the intent detection analysis. But indeed, we believe this direction needs more statistic and some A/B testing to see how this knowledge-based information can actually help. So finally, we have some take-home message in terms of a speech recognition task. So we find out ASR language model in turn for rescoring shows competitive result on improved word error rate reduction, and the subtask learning and the joint loss optimization are still open questions. For example, how to make it efficiently, how to make these things on device without latency is a big issue. And different feature encoder or weakly supervised methods can be further help if we don't really have a lot of NLU tags during this learning process. Another challenge could be the model capacity issues. Once we're trying to incorporate a lot of this sub-network and this sub-encoder, this model will become even larger. So I want to thank my mentors here, Linda, E, and Anchor, and my colleague in Amazon, Anirudh, Dennis, and Ivan. And thank you for listening. And yeah, so hope you enjoy this ASRU 2021. And see you in the poster session. And appreciate it for all the reference I mentioned here. Yeah, appreciate it.